Recording in progress.
Terry, we are ready to start when you're.
Okay, thank you very much.
Thanks, Terry.
So I see we have 34 participants online now. So can we just confirm we've got Jeff available, and I see Edward is also there as well.
Thank you very much. Thanks, Terry.
Thank you.
I see we have 34 participants. So let's confirm we've got Jeff. I see Edward is also as well.
Yeah, I see Jeff. I see Edward as well. Good. Excellent. So APNIC attendees, welcome to technical session 3, which has a very strong DNS theme. We'll be hearing from, of course, Jeff Houston and also Edward Lewis from ICANN. I think we've also got someone playing back my audio to me as well. So can we check that out?
Checking that. Yeah. Okay. It should be okay now, Terry.
Okay. Thank you. So one of the things about this session is we have 2 presenters. So that means we do actually have a bit of extra time for Q&A. With the Q&A, you'll see on the bottom of your Zoom window, you have a little pair of buttons there called Q&A. I would encourage you to put your questions in there as we hear the presentations. And I also would encourage you to check the Q&A from other participants and upvote the good questions, because it's always a good policy to have questions that are crowdsourced as opposed to trying to pick them up. I'll see some great questions and I'll obviously ask those of the panelists as we go, but please, if you do have great questions, please put them in there and upvote the ones you also think are great. But I see we have Jeff there looking impatient. So Jeff, when you're ready, please start talking to us about Oblivious DNS.
Thanks, Terry, and hi, everybody. Let me share my screen. Hopefully you can all see this now. Someone say yes.
Yes, Jeff.
Wonderful. Okay, let me move on, because I may only have half an hour and there's a fair few slides. So let's talk a little bit about DNS privacy. And I suppose the real question is, why pick on the DNS? Well, the issue is the DNS is a protocol from the 1970s. Well, actually it's from the 1980s, but it has a very similar history. DNS queries are open. They're not encrypted. It's a really simple UDP-based protocol. They're not secured. And when someone mucks around with the answer to your question, you can't tell. Completely undetectable. And bizarrely, DNS responses are actually basically predictable. And so if someone who isn't even on the path just hammers false answers at you, there's a strong chance you're going to pick one up as the answer to your previous question and believe it. So the DNS is incredibly vulnerable. As I said, I don't know where my queries go. You don't know where your queries go. And to be brutally frank, you don't know where your answers are coming from either. And so when tampering happens, it's extremely challenging to actually figure out that it's going on. And again, even though it's easy to play games with users, why should we play these games? What's the motivation? Well, you know, as you're probably aware, the internet is now almost the leading candidate in the surveillance economy. Almost everything we do on the internet is carefully observed. Our data exhaust fumes attract a panoply of sniffers who use this sort of digital detritus, the things that we do, in order to assemble an astonishingly accurate profile. And the DNS is one of the gold seams of this kind of data. Everything you do starts with a call on the DNS. And so if I see your queries of the DNS, I don't need to know anything else. I know you. And in this surveillance economy, this is incredibly valuable information. It's incredibly valuable information to a whole bunch of people, the Googles and Amazons and Apples of this world, Facebooks, etc. Absolutely. But as we saw with the Snowden revelations, it extends into nation states as well, who've taken DNS surveillance into a whole new level, according to the Snowden documents. So can we stop it? Can we stop folk from looking over our shoulder? The answer is, well, probably not. But can we make it harder? Ha ha ha. Well, yes, we can, and we are. And that's what we're going to talk about today. So securing the DNS, it almost seems like a bit of an anomaly. Is the domain name a secret? Well, no, because domain names are open information. Is the response a secret? Well, DNS authoritative servers are promiscuous answerers. They don't give an answer to you and a different answer to Fred and a different answer to Alice, etc. No, it's the same answer, more or less. And so neither the question or the answer is notionally a secret, steganography notwithstanding. So it's not that's the issue. What's the issue is that I am asking at a certain time. It's my interest right here, right now. It's me, and it's that question. So it's this metadata about my identity that comes from the IP packet header, the DNS question I'm asking, and the circumstances, previous queries, next queries, that actually betrays a huge amount of me. And that's the issue, rather than the fact that I queried for foo.bar for whatever reason. So let's talk about this, but first let's understand what the DNS is and what the DNS isn't. It's not this. It's more like this. The DNS infrastructure is incredibly complex. When you actually send your queries to 8.8.8.8, for example, Google's public DNS resolver, there's no single computer out there that is 8.8.8.8. There are hundreds of them all over the place. And there's front ends and back ends. There's various forms of caches in the middle, and there's a whole set of, if you will, infrastructure. Now, oddly enough, almost all of them have their vulnerabilities. My own laptop, bless its little heart, could be corrupted. I could be running some kind of spyware. The wire between me and the DNS recursive resolver or Wi-Fi connection, it's in the clear. It could be examined and intercepted. Someone could answer. My resolver that I use, and many ISPs have been found guilty of this, they sell the query logs. They leak queries. So other folk can look, and I don't even know. And all the way over in the servers leak queries for good and for bad. So all kinds of folk actually spread DNS information all over the place. And so it didn't take long for business models to be based on secondhand DNS queries. And if you've sat in any of the first forums this week, you'll notice there's a whole bunch of folk with their nose firmly glued on the DNS, looking for those evil DNS maldomains. The problem is, it doesn't matter what your motives are, good or bad. Sniffing is sniffing. An invasion of privacy is invasion of privacy, irrespective of the color of the hat you're wearing. And this is not good. So how can we make it better? How can we stop folk crowding around the digital exhaust pipe, sniffing these fumes? Well, let's talk about some of this. The first of these is Name Minimization. The DNS as originally devised was incredibly chatty, overly chatty. It sends the full domain name even up to the root service. So if you saw the queries at a root server, you actually have a huge amount of information about what end users like you and I are actually asking for. With Name Minimization, which over the last 2 years has certainly taken root in many DNS systems, it eliminates all of that extraneous information. Only send as little as possible. Now, the way it's actually implemented, it's only 3 labels deep. So if you have a.b.c.e.f.g.foo.bar, you're out of luck. Short names, foo.bar, www.example.com, yeah, they get minimized. So it certainly works. But oddly enough, it only works in the innards of the DNS, recursive to authoritative, deep in the middle of the DNS infrastructure. End users like you and I, nah, we send the recursive the full name. So it's actually not security for you and I, it's security for the middle. Dns Sec, or as some folk talk about it, Dns Sec pixie dust, because obviously it makes everything better. It's actually a really cool technology. It's all about digital signatures, and it makes sure that the answer you get is authentic. It's the genuine answer. It can't be denied. And in essence, if someone's trying to fiddle, you'll see it because the signatures won't match. So a modified result, even one that says, no such domain, you can detect that's a lie if the domain really exists, if the zone has been DNS Sec signed and you ask the query using the magic incantations of DNS Sec. You use the extended DNS fields and set the DNS Sec OK bit. The zone needs to be signed, and then you can do your validation and check that all the digital signatures match. And if it doesn't match, don't believe it, because it's a lie. It sounds fantastic, but everyone's got to sign. It's one of those all-in things. I can sign my zone, potteroo.net, but if .net isn't signed, I'm wasting my time. So all your parents need to be signed. Now, the root's signed, most, not all, most of the top level domain names are signed, and it's sort of slowly permeating through. But in the entire world of DNS names, hundreds of millions of names, the best estimates are that 7-8% of domain names actually are DNS Sec signed, and the other 92-93%, doesn't work. But it's worse than that, because I don't, well, actually I do now, but you don't, validate the answers on your end device. You just send a query to a recursive resolver and it sends you back an answer. You're trusting it to do validation, if indeed it does it. If the recursive resolver wants to lie at you, and some do, you can't tell, because if you're not validating, you lose. And why do I do validation and you don't right here at the end device? Because I'm patient. I'm very patient. I'm willing to run a slower DNS than you, because stub resolvers, things that sit inside your end machines, don't normally do validation because it's tediously slow at times, too slow. So if we outsource it down into the recursives, it's probably faster. So what if we want to make this surveillance work harder? Well, we really need to encrypt like crazy. And while some folk might say, let's all use IPsec, no, seriously, no. Don't ever use IPsec, ever. These days, it's all about session level security or transport level security, or TLS for short. Now, the first of these was actually DNS over TLS. Now, the DNS can run over TCP. It's all part of the spec. But what if that TCP actually does a TLS handshake and sets up a secure encrypted session. All the DNS works the same because it doesn't actually really care about the lower levels. And dot then sets up this persistent relationship between my machine and the recursive resolver, and I send all my queries through it. So the setup cost, although it's a few round trip times, can be amortized over a whole bunch of subsequent queries. And by the time I've got it running, it's probably no slower than DNS over UDP for me. And there are a couple of things that happen in TLS which are really quite cool. I can authenticate whom I'm talking to. So if I want to talk to Google's public DNS and no one else, TLS will actually give me that assurance I'm talking to whom I intended to talk to. And secondly, no one else can see. So if anyone wants to sniff what's going on between me and my chosen recursive, no such luck. However, not perfect. The IETF in its infinite wisdom decided to give it a special port 853. So you only need to sniff the wire to see that I'm using DNS over TLS because nothing else uses UDP port 853. Oops. Easy to block. Oops. It's expensive. TCP basically reduces the throughput on a recursive resolver by up to 60%. So yes, there's a huge greater load in the DNS to make this happen. And quite frankly, if I do a secure session to Google, no one else can see it, but Google still knows all about me. And it's kind of no one else knows, but Google knows too much. Oops. And until we get encrypted client hello in TLS 1.3, don't hold your breath, then quite frankly, even a wiretapper can see who I am talking to, which is still not good. Yay, bring on encrypted client hello. We're waiting. Not content with that, we went further and did DNS over HTTPS. Now it's almost the same as DNS over TLS. HTTPS, TLS, the only difference is we're framing the object in HTTP semantics and we're changing the port number. So now I'm hiding in all that other HTTPS traffic in port 443. And I'm using, though, DNS wire format. Why would I want to use DOE over DOT? Well, interestingly, I don't have to use the built-in DNS stub resolver run by my platform. I don't even know if Apple get the logs from this device and send it back to the mothership in Cupertino. They might not. I can't tell. Whatever's going on in there, it's a secret. But what if my application says, don't trust you? I'm going to do my DNS as me. I'm going to make my own HTTP connections as applications do and just not even tell the platform what's going on. So that stub resolver function can be lifted up and made into an application. And so I get even better privacy. I even get privacy from my platform, which you really shouldn't trust if you're really quite paranoid. And I don't have to wait for Apple to introduce the next upgrade, the next this, the next that. My app can control its own security and its own destiny. And that's where we're going these days. Apps are actually running the internet rather than platforms or networks. And so this is just one more logical progression. So why run DOE? Well, port 443, that's good. There are some issues with DOE about giving you the answer before you even asked. Resolverless DNS. And that's certainly an interesting concept, and we're not quite sure if it will be useful or abused. But certainly you can hide. You can hide very, very well. And if you're a bad person, that's not a good thing. If, on the other hand, you want to hide from bad people who want to look at you, well, that's a good thing. And it's hard to tell which is relatively better, which is relatively worse. When I said DNS over HTTPS, I didn't say whether it was HTTPS 2 or HTTPS 3. And DNS doesn't care. And if I'm talking about 3, it actually includes the quick transport protocol. Now, that may happen automatically, or I could, in the latest set of standards, use DNS over quick directly, which is the thin encrypted UDP shim. So it's sort of in between DNS and the transport, then instead of just basic port 53, I go and use UDP port, or let's say 443, or maybe 53, who knows? It's up to you, really. And actually run encrypted UDP and put my DNS over that. UDP port 443 isn't universally accepted. A whole bunch of folk don't like Quick. Even though Facebook's now running it, they're still going, don't like Quick, yay. So it does have its issues, and there is some port blocking middleware, but by and large, they're all very similar. Now, the way this kind of works is it's best to use these kinds of protocols to a busy open resolver, because no third party can see you. So many other folk are using that busy open resolver that your responses, where the resolver is trying to resolve your name to authoritatives, is largely lost in the noise. And quite frankly, it's extremely challenging to actually backtrace individual users. So, and here's the bargain with the devil. You've got to trust one of the big open DNS resolvers, whether it's Google, OpenDNS, Cloudflare, Quad9, with all of your secrets, and run DOH or DOT to them. And then you're doing a tolerably good job in hiding in the crowd. But that first part of the bargain, I've got to trust Google. You're right. I've got to trust the very folk who are experts in assembling my profile. Oddly enough, I'm still uncomfortable. Quite frankly, I don't pay Google. I don't have a contract with them. I don't even know which country's laws Google obey. So why am I protected? I don't think I am. So can we do better? There are two proposals out there that I've found absolutely fascinating. The first one is a thing called Oblivious DNS that encrypts the original query name into a new query name. Oh my God. Let's look at this in this little diagram. Hang on, it's a bit weird. So here am I, the client, and I want to go to www.example.com. So what I do is I generate, let's call it a session key, and let's call it K. And let's go and encrypt www.example.com, the full domain name, using that key, right? Now, I'm going to take the public key of an ODNS recursive resolver, the public key, and I'm going to encrypt my session key with its public key. And then I'm going to push all of that into a domain name. So it's just basically digital noise. And I'm going to append the label ODNS and just hand it to my recursive resolver. Now, my recursive resolver sees a bunch of digital noise.odns. Even if there was a cached entry, it would just answer it from its cache and the answer would be good. Bizarre. But if there isn't a cached entry for that odd name, it just goes and sends it to the ODNS server, who happens to have the private key to decrypt PK of K, which gives it K, which can decrypt the query name, and then it flips modes, becomes a recursive, resolves the name, and then you send it all the way back. It's brilliant, but it's still the DNS over UDP over port 53. But oddly enough, if you really want to get cute, you can do that first step over DOT, DOH, DOQ, DO anything, and it would still be cool. But the issue is trying to encrypt all that into an existing label is a lot of squeezing and stuffing, and that doesn't really work that well. So can we do it slightly differently? And this is the latest one called Oblivious DNS, which doesn't play with the query name, which I thought was really cute. What it does do is a more conventional TLS in TLS. This diagram will help. So the user encrypts using TLS a session to a proxy. Now, what you also do is take the key of your target and encrypt the query. So what the proxy does is take your query and strips out your identity and re-queries on your behalf and sends that to the DNS server, who can now decrypt it. Now, what does the server know? The server knows what I asked for, but it doesn't know my identity. All it knows is a proxy asked for that query name. So the server can't put me and what I'm asking for together because it doesn't know my identity. Well, what about the proxy? It knows me, but the query is encrypted and it doesn't have the key. So it can't put me and what I'm asking for together either. And so oddly enough, nobody else knows that I asked for that name. It's completely hidden. Now, there's one thing about this that's kind of crucial. These two boxes, the proxy and the server, must never, ever, ever take their logs and match them. They can't collude, because as soon as they collude, all the benefits of this are completely lost. But other than that, it's really cool. Now, where's this heading? In the last couple of seconds, I'll try and explore this a little bit. The first thing you've got to understand is that in terms of economics, the DNS is a wasteland. I don't pay for queries. You don't pay for queries. Who funds all this? Well, my ISP funds a lot of it, and it sort of comes out of what I pay them. But what about those open DNS resolvers? Who funds them? Not me, not you. And so interestingly, it's very difficult to make the DNS, particularly in serving queries, spin money. Folk have tried to substitute NX domains with answers to search engines, and to say it was viewed with extreme disfavor is actually being polite. If you do a good job as an open resolver, all you do is spend more money because more people use you and you've got a bigger funding problem. So in some ways, improving the DNS is a labor of love. It's not a labor for wealth and profit. And so what actually happens is that most folk just simply use their ISP's resolver because that's the one you're paying for, and that's the one person who actually has an obligation to do this for you. But if you make it more difficult, if you make your ISP run DOQ and DOH and DO anything else, all they do is spend more money. I don't pay them any more money. I'm not going to remain a customer just because they do that. So oddly enough, I'm expecting them to spend more money and get nothing for it. And so for ISPs, the DNS becomes a part of Mr. Cost. It's not Mr. Income. And so there's a lot of resistance to making Mr. Cost grow bigger because that's the way you basically kill your business. So interestingly, the DNS is highly resistant to change. And all these privacy movements sound great, but the problem is who's going to pay? Now, that means that I think open DNS will be here for a long time yet. So all those folk who think, oh my God, my view of the DNS is dying, I won't see all these evil DNS names, calm down, nothing's going to happen. And quite frankly, users don't play with the buttons. So even though anyone could, in theory, change their DNS resolver to all 8s or all 1s or all anything else, most folk don't. And that's probably a good thing because fixing up those mistakes can be incredibly detailed. So by and large, open DNS resolvers aren't really going to take the DNS and run away over the hills. But there is one place that I think it's going to change. Applications are increasingly impatient with the rest of us. They're impatient with platforms that only upgrade twice a year. They're impatient with corrupted old shareware libraries that really don't work very well. And they'd actually like to take more of their fate in their own hands. They don't want to use the platform. They want to do it themselves. In the same way that Quick runs inside the user space, all the transport protocol is inside the application running Quick. Applications now want to do it themselves. They want to fund their own DNS privacy infrastructure. They don't want to wait for you to press a button. They don't want to wait for your ISP to do something. They don't want to wait. And because applications is where there's money, applications is where there's a need, and if you will, funding to meet that need. So applications that divorce themselves from the DNS infrastructure as we know it is an inevitable and near-term future. So it's still going to be the DNS, but it's not going to be the one that you knew or the one I knew. Because this progression from network-centric service through platform-centric to application-centric services is being played out right now in front of our very eyes. And the DNS is being swept up with this. And almost every single part of the DNS changes as soon as the DNS becomes sucked into application space. Single coherent namespace, nah, historical rubbish. Because the entire namespace then becomes application-centric, and different applications will have a different namespace to suit their needs. Now, we blew up addresses when we ran out of v4, and because you're not running v6, we don't have a coherent address space. Oops. And now we're going to blow up the namespace because we've all got bored with one namespace and it kind of sucks and it leaks like a sieve. So we're going to have lots of little namespaces and it'll all work, right? Yeah, right. Going to be fun. Strap in. Thank you.
Oh, thank you, Jeff. That actually has me thinking about a few interesting questions straight up. But one thing that I find interesting in all this is the privacy issues. Obviously, if you're using an open resolver, someone's using that data. What are they doing with that data?
Oh, the names you ask for, and when you ask for them, say an awful lot about you, say an awful lot about us, say an awful lot about what memes are hot, what products are hot, whether the ad campaign is working, and all that essential feedback to say, is my advertising campaign reaching the right target? What do people think? And so on. Because as soon as you get something interesting, you put it in the Google search engine, that gets you a bunch of sites, you asked for domain names, the network betrays you. You're leaving big, filthy, muddy footprints on the carpet, mate. We can see where you're going. And that's the problem.
So it generates very useful data for them to plug into their business model, obviously.
Real-time data, right here, right now. Not last week, not last month, this second.
Yep.
You couldn't get more valuable.
And we have a question here from Owen Baker. I suppose if applications want to fund their own DNS privacy, they should also fund their own DNS snooping. Now, that's an interesting proposition, isn't it?
Why did Facebook create an application on my digital thing that's literally hundreds of megabits big? Because inside that app is an entire operating system. How much does it leak to Google, Android, or Apple's iOS in terms of information? Well, as little as possible. It emits raw IP. It doesn't even use the platform's transport. Why does it do this? Because Facebook is paranoid about a number of things. It's paranoid about the platform snooping on it. It's paranoid about other applications on the same platform snooping on the Facebook app. And Facebook is incredibly valuable. It spent a lot of time and money understanding me and assembling a profile of me that it can sell to advertisers. The last thing it wants to do is to give any of that information away to anyone else. It's their data. And so what you're seeing is not only an internet full of applications that are increasingly taking on responsibility, you're also seeing an internet that is increasingly full of paranoid applications that want to shutter themselves up, not only from third-party onlookers on the wire, but that application just over there that I'm sharing memory space with, I don't trust it. And that's what we're seeing.
So do we have any more questions, or shall we move on to Ed?
I will hand you back a screen, Terry. Thank you very much, and thanks all. Bye.
So next up is Ed Lewis from ICANN. Ed's going to be talking about the one thing we touched on just before, DNS Sec, but essentially tracking when zones are signed and actually extracting, and again, extracting some data from activity on DNS. So very interesting, Ed. Thank you.
Sure, I'm setting my screen up now. And can you see it? Can you see it here?
Thank you.
Okay, good. Let's see, let me clean up here. and start my timer so I know where I'm talking. Okay, so I'm going to talk about something I've been working on for quite a long time with Dns Key Life Cycles. I'll talk about why I'm looking at this, some about how I developed these visualizations and some samples of the visualizations, and I'll go through those towards the end. So yeah, I started in on DNS Sec as a protocol developer. I was someone who thought about what should we do with this. I wasn't the original developer of it, but I was early on in the development of the protocol. And so in the process, we had a lot of ideas of what this would be used for in the future. We tried to imagine what operators would go through doing this and try to make it useful or workable in operations. We actually tried. But as you've heard in Jeff's talk, that we weren't all that successful. And so I spent a lot of time pondering this and trying to figure out why is adoption slow, why is deployment slow. And after studying for a long time, I realized that I was looking at a classic case of something called Devops. And Devops is a buzzword for the developers versus operators interface that we see in many examples of out there in technology land. Developers tend to love to produce very complete solutions, and complete might be complex. It could be, we think of it as versatile, but they think of it as complex. Operators, on the other hand, have a whole different set of goals out there. They like to make sure that routine tasks are performed reliably and repeatedly over and over again. Repeatable processes are needed, simple tools are needed. I remember giving a talk on this almost a decade ago when an operator once told me, actually on top of a castle somewhere, we use tools, we don't write software. And that was an eye-opener to me. So with that as kind of a background for where this sits in this realm of things to look at, DNS Sec has slowly developed. It was designed to be versatile and anticipate many situations out there, but apparently it's the operator friendliness we thought we put into it are not very operationally friendly. And so it would be a really good idea to figure out what's useful and what was not so useful. So, this is why I want to dive into study this thing a long time ago. So there are three things about key life cycles that go into this work. One thing about DNS Sec, which starts with private-public key pairs. There's a private key and a public key out there, and they're used. I think many people are aware of how they're used nowadays with the signing digital signatures. But DNS also has a cache system. We have that fuzziness. In fact, you saw Jeff's his great cartoon of the resolution process out there. It's just, when you change something at the source, the outside of it sees that change after a couple renditions, some time later, basically. Things are fuzzy in that way. And also DNS management is very hierarchical. You have to, every operator of the DNS, every runner of the DNS zone has someone they report to. It goes from, someone at an enterprise that has a address somewhere in a TLD, goes to their top level domain registry. They're the boss of them, and above them is IANA running the root zone. And if you actually extend it further, the boss of IANA are all the people in the world who rely on what IANA puts out there. So we have these three things feeding into how keys are designed for DNS Sec. Now, as a result of all that, DNS Sec keys have lifetimes that go through a few discrete states. If you were to hand wave at a very high level, we have a time when keys are pre-published. They're made available in the DNS so that the caches can fill up with them before we actually see signatures. There's a period of time when the signatures are actually active, that they're being generated and being validated with the key. And then because signatures will sit around in caches even after you stop using a key, we have to keep publishing the key for some time to make sure those old signatures can be validated when they're needed to be validated. Now, all of this can be seen in a zone. The keys have to be published. They're seen widely. People ask for data all the time. So we could actually take a look at this stuff. Now, a key lifecycle is measurable, but what does it mean? It's easy to imagine that we can see what the keys go through, but why? Why bother? Well, one thing about key management is a strong component of how DNS Sec is operated. By looking how keys are managed, you can tell quite a bit about how operators go about their work. For example, the first blush at some of these pictures, you'll see that there's some very regular cycles. Some operators will change a key every month, every quarter, and so on. And that indicates usually a lot of automation. And automation is a hallmark of a pretty mature operational practice. It's not someone doing it as a hobby. It's someone who's put all of these cycles into a computer script somewhere and they let it run 24/7 and so on. On the other hand, when you see some of these pictures that show disruptions, and I don't have a whole lot of examples of that, but there are a few that I'll show, you realize that the operations were disrupted somehow. Either there were changes in the operator, there were changes in what they thought about their operations. They've actually refactored things. Sometimes it's a operator who's doing a really good job, but decides that they're spending too much time on DNS Sec and they want to back things off. It's a very interesting way to just take a look at what's going on somewhere and see what's going on in there, and looking for patterns too to see what else is out there. Now, one thing I should caution is that when I talk about disruptions, it doesn't mean emergencies. In fact, in some of the charts that one of the charts I show, it looks like there's a period of time when the keys were dropped out, but there wasn't a dropout. It just shifted around, and if you trace it just right, you see that they were always validating or signing correctly, just that it was not done in the way you might expect an operator to do that. And again, the word expect is in terms of probably the developer of the protocol. So again, back to the DevOps notion, and I've probably we've gone through many of these cases already. It lets us, what I really want to do is I want to strengthen the protocol elements that were operator friendly. I want to make sure that if we've developed a protocol, an extension of protocol that was well adopted, it probably did something good there. We want to get rid of protocol elements that are not very friendly. So this is a good way of going back on, did we do a good job of developing the protocol? I also use this to identify the incidents. It's good to follow up with operators one-on-one, and there have been times in the past when that's been done. It's been a little less frequent in the last couple of years, especially as these visualizations came out, unfortunately. And again, I caution that as you look through these things, judging service level, how performance has gone, is really tricky, because what I've learned from looking at operations is that what's on the outside doesn't always tell you what's going on the inside, and whether what's on the outside is actually a problem or not, because you never know what the requirements were around these situations. So the good question here is, how do we actually do this? How do you try to visualize anything? The key element here is having data. So we have been able to track what happens to TLDs now for now more than 10 years. I passed the 10-year mark earlier this year in daily observations of what TLDs have been publishing in their zones. It doesn't take a lot to get a good idea of how DNS Sec is running. There are a few key records, a few important records, and they're all at the top of the zone. They don't look at the contents of the zone. They don't try to get into the size of the zone or any other business type of relationships or even performance. I don't look at query rates. I don't look at a lot of live data, but just look at what's published. It's very static. What are they publishing at the root zone? Probably the biggest issue over the years is that it used to be very convenient with the any query to grab all this information. Now, since that's no longer a liked query type, we have to look at the records piece by piece to see what's out there. Now, to measure DNS Sec, to measure the keys themselves, it turns out that you only really need to look at 4 different records in the apex of the zone. The apex of the zone being the name that the zone is named. So you have examples, it's apex. There are only four types of records I need to look at here, and I also include in that some assumptions. I look at the DNS key record, of course, that tells me when a key is actually published, because that's the record which actually reveals the public key that's useful for the validation process. I look at the DS record. That's the record at the parent that says that which DS record is actually in play to build the chain of trust. And then I can look at the signature record over the DNS key set. The DNS keys, some of the keys only sign the key set itself, the KSKs, the key signing keys. And so by looking at that signature, when it's there, we know that KSK is actually doing something. It's providing a service to DNS Sec. It tells me something about Ksk Life Cycles. And then finally, I look at the signature record that covers the SOA record. This is kind of where the assumption comes into play, because generally you can sign different records in the zone with different keys. That's part of the protocol. But the truth is that in the TLD situation, whatever signing the SOA record is going to be the one active key for the entire zone. There could be multiple keys, but generally just one. And whatever it is, it's going to sign the SOA record. And secondly, since I'm looking for the entire time that the key is in play, every time that key signs something, the SOA record has to be updated because the serial number changes. So again, I just look at the resource record of the SOA record. The signature of the SOA record to determine when a zone signing key, the ZSK, is in use. So I've talked a little bit about KSK and ZSK already. ZSK, that's the zone signing key. Those are the keys that are used by an operator generally to sign the zone all in-house. It's just an in-house operation. The key signs all the data that I have in there, and I publish that, and that's all there is. Because simple, there's generally one model of how they're used. The Ksk life cycles are more complicated because they certainly because they involve two operators. Each operator has a parent, and I have TLDs to IANA to all the validating resolvers out there. And whenever you have two operators doing their thing, it's hard to get them to work in unison, especially especially when the situation is you have one TLD talking to IANA. That's fine, but you have actually many TLDs talking to IANA, so you can't really get them all to work together. And then down the tree, all of the customers of TLDs, they're not going to be able to change everything at the same time. And in fact, if they did, we'd have this huge clump of activity around the time of key change. We don't want that. We don't have that. So that's what the Ksk life cycles will be, why there's so many of them. So to picture what I'm talking about here, the states the key goes through, when it's created, you don't see it. We put the key in the zone. It goes into preview at the bottom here. After that, we add the signature record. It becomes actively used. We see the key is actually being used. We remove the SOA record at some point. The key goes into retirement or the post view. And then we discard it when the key is pulled out. That's a pretty simple model. The ZSK, a little more complicated. This is one version of it where I can publish the key, put it into preview, add the signature, make it a key is what I call unchained because now the key is only working locally. I add a DS record to parent, and this is the external action, and it becomes an active key, and that's where you really want it's doing its work. At some point, the DS record could be pulled out. It becomes unchained, meaning it's no longer doing the chaining work. Pull out the signature record, and I might revoke it, or I might just pull the key out, and I pull the key out, discard it, and it goes out. Now, what's more common is this case where I put the key and the signature at the same time because of the mechanics of the Ksk record. Created goes unchained, which is basically the preview in some sense. I add the DS record to parent, it gets chained, unchained, and so on through its life cycle. But because we sometimes see the multiple operator situation here, sometimes these two steps, the taking the DS out and taking the key out, flip in order. And you wind up sometimes having a key pulled out of the local zone with the DS record still at the parent. I call it kind of a dangling situation when the key is just, the DS record is just kind of extra weight at the parent, but not harmful because it's not doing any work before it gets taken out. So the Ksk has more options out there. So to step into some of the visualizations, which is what I really wanted to highlight in the talk, I have to do a little bit of background of the root zone. I'm going to talk about the root zone as that's the cleanest example I can talk about without picking out anyone, being more specific about anything. And this root zone, it uses ZSKs that are published 4 times a year. Every 90 days, they rotate the zone signing key. So for example, from April 1st to July 1st, there will be a key in play with an active key. And for about 10 to 12 days earlier, it'll be pre-published. The 10 to 12 days are just the way we manage the calendar, and the uncertainty has to do with the fact that not every calendar quarter has the same number of days. At the end of the quarter, in July here, I show a 10-day period where the key is in retirement before it's being taken out. And I'm going to come to a chart sooner or later that will highlight how this is seen in actual use. And I'll also look at the changing of the Ksk and the lengthening of the ZSK, 2 actions that happened in the past. So this is the visualization, and I have to apologize. I think these slides don't really do justice for some of what this visualization can do because of the form factor and the limitations on bandwidth and whatnot. But this is the overall look at the root zone. This shows the Ksk. There's only been 2 over time. There was the original one that was started before the data began, which is over here. And in 2017, we introduced this replacement key, and it took over late in 2018. Meanwhile, down here, it's very hard to see here, so I'll have to blow these things up, and blowing up by expanding the time. The ZSK has been changed quite regularly. Looking at the ZSK in particular for 1 quarter from March to July of this year, this key 14631 shows its life cycle. And in the beginning here, that's the preview period of time. It's a lighter shade of green. And if you zoom in on that, I can show that it's actually the dates that were predicted, the 22nd. This is all data generated, not a design document, by the way. The 22nd of March, it appeared. On the 1st of April, it went from the preview mode into its regular lifetime, which goes off to the side. Meanwhile, the Ksk did not change in any of this. Following the preview period, there was an active signing period of time. And then it goes into the retirement phase where I have used a darker green to denote that. So that is a quick example of the ZSK's life cycle. The Ksk life cycles are very hard to see because they're so long for the root zone. But here is a period of time of great interest a couple of years ago, which is the Ksk rollover, which showed that beginning in July of 2017, we introduced a new key that sat out there for a long time, and it was elongated because we were concerned about the key being pushed to all the resolvers out there. The plan was actually to be 1 year shorter, so that this line here should have come right about there, but we lengthened it by a year. And I'll blow up the tail end of this to show some of the action that happened down the end. While this is happening in the Ksk, the ZSKs went chunking along in their usual light green to middle green to dark green life cycles, a preview, active, post, and we have made sure we didn't make changes to that while we changed the Ksk. And these slides actually bear out all the plans that we had and actually what happened. Now, if I look at the tail end, I get to the exciting part here for some people, the revocation. This is when we revoked the Ksk for some time, and that was from January to April. There was a time when the key remained in the zone, but it was just not being used. It was not generating signatures for some time because of the way we worked the size of the messages out there. And again, down here, you see the ZSK was going again at the same times. So another thing I wanted to highlight, it used to be a little more visible. It turns out the longer this experiment runs, the harder it is to see events because the time just washes over things. But there was a time when we changed the length of the ZSK for the root zone. It was 1024 bits originally of an RSA SHA-256 key, and it was expanded to 2048 bits in 2016. And what I wanted to highlight here was that in most cases, we have a period of time where the retirement is fairly short. It's very regular, but here we lengthened it because there was a worry about fallback. Now, we didn't need to get fallback, but that was the one time that the fallback, that period of time actually was extended. Excuse me for that. I need to cough. Sorry, it's late here for me. So some other examples. This is a large Gtld, one of the legacy Gtlds out there, which shows that they actually I went two slides, that they have had one Ksk for the lifetime of the data, and they've had a very steady progression of Ksk or ZSKs going, but they have changed the length of their ZSK at one point. If I look at that period of try to focus in on that change again, when they made the change, the only alteration to all of this was that that we kept the ZSK around a little bit longer, or they kept the ZSK around a little bit longer in case I had to go back. There's a lot of concerns about the lengthening of the increasing size of the DNS message responses. Gtldb, this is another one of the 3 earlier legacy operators out there, and they've been a bit more active with the Ksk. You see up here a lot more charts. The colors here actually signify which algorithm was in use. They had been using RSA SHA-1 until just recently. They crossed the line up into RSA SHA-256. They've been doing some refactoring of their operations. They had a They had a very long-lived use Ksk, but it was regularly rolled. They had also always had a backup one out there. And down here, ZSKs actually exist. And because this chart shows on my screen a blank area here, I redrew the chart. This is the same chart. I just changed the way it's drawn. And there is a period of time with the ZSKs actually are there all the way through. But what is interesting here is that besides being very regular in the way they've operated the ZSK for many years, there were 2 years where they seemed to pause their activity, but then they resumed going back to a very active way of rolling keys and so on. And probably we'll see some more changes up here as more and more refactoring goes of the DNS Sec implementation they have. And I use this as the first example of operators do change their minds over time. And that's probably something that we hadn't really thought about, but operators will refactor and go back and redesign how they do things. And again, there was a third of the old legacy GTLD operators out here. And this is another one which had a very regular cadence for a long time, both in Ksk and quite actively in changing it, and ZSK also. But then at some point, something changed here. In fact, this red bar, which the red bar doesn't mean a problem, it just means that there was something of interest happened here. In this case, I believe it was that DS record hung around at IANA for longer than it needed. The key had gone away, but it was dangling there for some time. Meanwhile, all the work was being done by this key up here, so there was no validation error. But it shows that something happened here with transitioning the back end of the registry. And in fact, I don't know what the story is, but it's just interesting. I would go back and I would do some ask people if there were interesting stories about that at some point. So Cctlds, there's a lot more Cctlds than GTLD operators out there, frankly. Cctlds tend to be more like one or two TLD shops out there. And this is one Cctld I had my eye on for the longest time as someone looking at data. Early on, they did something interesting here. They actually implemented automated updates of DNS Sec trust anchors, otherwise known as RFC 5011. They're one of the 2 operators that actually were bold enough to deploy that. And they did it for a couple of years, but then things changed. And you can see it mostly in the Ksk by these different size charts. It kind of lost the operational cadence out here. And up here, totally, it looks like it's just stayed with one key for some time. I do know how, I have some other information about this, but early on, the person who was in charge with this was someone really interested in making a very good engineering, very in-depth operations environment. But when that person moved on and this went to an operations staff, it was handing keys to a homemade car to some people who were professional drivers, and they didn't know about all the features under the hood. And basically, that's an operational nightmare when you don't know what's going on in there. It's not the operator's fault. The operators are doing operations, but they weren't sure of all the things that were happening during the time of this person. Maybe a lack of documentation. I don't know. I didn't go through all that. But if you look down in the ZSK, you see also there's some other signs of things were changing here and there. Now, finally, I have another GTLD that I like to highlight because this one has done something that many people felt was very difficult, and they've done it twice. They changed their security algorithm. They changed the key algorithm from RSA SHA-1 to 256, which you saw earlier that the second GTLD operator has done that. But this was the first, these were actually the first team to do this. I know it's mostly the anecdotal data that they were the first to change their security algorithm. And they did it quite a long time ago. They were kind of pioneers in that way. But what I hadn't realized was that they also changed again more recently to elliptic curve from the RSA protocols altogether. And that had raised no real interest, and there's been quite a few of those transitions over time. But they're, and amazingly, they have been very much like clockwork in both of the keys out there. So one thing I actually and I dug in a little bit deeper because I was really amazed to see this, but these charts, these are 2 charts spread out over time. This was 2014 or 2012 rather, and 2018 when they did the 2 rolls, and they rolled from RSA SHA-1 to 256, and RC Geometry 6 went over to the elliptic curve algorithm up here, and it shows that they used the same process. In fact, it was almost to the same day for all these things, except that they were years apart. There was a 1 day difference in here, and I haven't figured out why that 1 day difference existed, meaning being that they both started on November 14th here and there. They ended on January 16th in and January 15th there. I was curious, was it the day of the week? Was it, what was going on out there? And I would love to ask the question of the people, but I haven't been able to travel and say, what's going on? Which would be more polite in person than remotely. So to wrap this up, right now the visualizations are not publicly available, but you can ask me if you want a blow up of something for a period of time for on demand. It's easier to do it that way right now. I really wish I had a way to deliver this in other ways, but we don't have that. When travel resumes, I would like to get the story behind the story for some of these out there, things I've been seeing out there. And I'd still like to dive into Devops. I'd like to find out what can be done as a developer to help the operations situation out more. I'm looking as far as these visualizations, these are done like one-on-one. They're not usually groups of things. I can't look at groups of operators out there. But I'd like to figure out what's a better way to look at some of these cycles across basically maybe even all the TLDs of a certain operator. And still trying to get to the basic question was, how long should a key be used? Or more likely, what do operators think is the right amount of time for a key? As you can see, the difficulty there has been that as they change their minds, it's very hard to do that programmatically and just pull it out of the data. So with that, I will ask our moderator to let me know what's next. Questions?
What I'm actually looking for now is questions from the audience. But what I found fascinating with the talk, Ed, is that there seems to be an operational narrative that's hidden from us in all this, isn't there? And it's very different from TLD to TLD as well. So yeah, if you do get a chance to catch up with these people and find out what was going on at the time, what was happening, it'd be great stories to be told for sure.
Yeah, I have some experience with that, so I know there's a lot more to mine out of that. And to tell you the truth, what really triggered my seeing it this way was looking at the deployment of the route origination attestations.
Mm.
Looking at deployments of anything, there's a lot in there.
Yeah, that actually brings a lot to the fore about if these particular operational issues should be standardized. Maybe someone out there in IETF land can write the right RFC or the right BCP to cover all this. So everyone has a playbook from now on. So yeah, fascinating. So does anyone else have any questions? Raise a hand, throw a question into the dialogue. If not, I'll give you another 10 seconds or so. But if not, we are actually 1 minute over time already. And I'd like to thank Jeff and also thank Ed for your contributions today. As usual, Jeff is great for a bit of doom and gloom. Thank you, Jeff. And Ed, I'm absolutely fascinated by these operational stories. I'm going to catch up with you later on and find out if we can get some more information out of you for the next set of conference talks that come along. But otherwise, we have the poll up, guys. Thank you very much for attending today and excellent work. Thank you.
And thank you, Terry, for the excellent moderation as well. And thanks to all the participants for joining this session. We'll take a short break and hope you can join the next one. Thank you all.